Hi everyone, this is Matt 2's show and Intro Stats, and today we're looking at a problem from my book, Introduction to Statistics for Community College Teachers. This is section 3F, number 13, so let's take a look at it. It says, according to the National Association of College Stores, digital textbooks are projected to account for approximately 13% of course materials sold by fall 2012. In a random sample of 260 college course materials, 39 of them, which is about 15%, 39 divided by 260, of the sample course materials were digital. Use the random sample data at 10% significance level and StatKey to test the claim that 13% of course materials are digital. Okay, so it gives us a little information about what to click on when we go to StatKey and how to put in the data, how to get the p-value. Okay, so it looks like we're doing a randomization hypothesis test. So it's not a traditional hypothesis test, where we'll actually be using random simulation. All right, so let's take a look. So the first thing we wanted to get at is, what's the claim? What do they think is true? So it says here that we're testing the claim that 13% of course materials are digital. So it doesn't say more than 13%, doesn't say less than 13%. So it looks like our claim is just equal to 13%. So remember, when you're doing these kind of tests, well, the first thing you do is to figure out what your null and alternative hypotheses are, and what kind of test are you doing. Again, this looks like percentages, right? One single percentage or proportion, and and we're dealing with the claim of 13%. All right, so I'm going to write that down. So I'm going to write, you could use P or pi. Some textbooks use pi. The old books use pi. Some newer books use p for population percentage or population proportion. So pi equals 0.13 is my claim. So I wrote that down right here. See, pi equals 0.13. Again, write down your claim. Don't get in a hurry to write down the null and alternative, H0, HA. Always start with your claim. Now, what about the opposing view? If they're wrong, what's correct? You know, if that claim is wrong, what's the opposite? So they didn't specify that they just think it might be bigger or smaller. They just said equal to. So the opposite of equal to would be not equal to. So what we're going to write now is the opposite of the claim. Pi is not equal. The population proportion is not equal to 13%. Now this would be a two-tailed test. It's a one proportion test, one population proportion test, and the alternative hypothesis is not equal, so it's going to be a two-tailed test. That makes it a little more tricky when we're dealing with the p-value. Okay, so now I decide which is the null and which is the alternative. Remember, the equal to claim has nothing to do with it. Claim can be the null or the alternative. It's the sign. Equal to or something with equal to is always the null. Anything symbol that doesn't have an equal to is always alternative. So I know the first one here, equal to, has got to be the null. So I'm going to put H0 next to that. And then the one that doesn't have equal to must be the alternative hypothesis. So I'm going to put HA next to that. So now I got my null and alternative hypothesis. I know this is a two-tailed test, right? It's a one population proportion test, but it's a two-tailed test. All right, so now we want to check the assumptions. They told us to check the assumptions. So the sample data should be collected randomly or be representative of the population. Yes, they said in the problem that data was collected randomly. Data values within the sample should be independent of each other. That's a tricky one. Again, we may be getting materials from the same author or the same publisher. So it may not be totally independent of each other. You know, certain publishers have similar policies, authors tend to write similarly. So, okay, so we'll go ahead and proceed with the test with kind of a question mark about independence. Independence is a tricky one to kind of figure out. We'll go ahead and assume that they are independent for now. All right. If it's a random sample from a really, really big population, like if there was, you know, if we were talking about tens of thousands or 20,000 or 100,000 books, and we randomly chose 260, then there's probably not a big, you know, the chances of us getting the same publisher, same author wouldn't be very high. So that would probably be okay with independence, but because this is probably a smaller population, I'm thinking that probably some of these books had the same publisher or same author. Okay, so let's go now and see if we can do the test. So the problem said that we're doing the test of 13%. We're using a 10% significance level, and our data, our random sample data, was 39 digital materials out of a total of 260. Okay, so it tells us to go to edit data, randomization hypothesis test, test for single proportion, edit data. Okay, so let's take a look. So this is StatKey. Again, we go to lock5stat.com, and it's a great program. I really like it a lot. We're going to click StatKey, and here's our randomized hypothesis test right here. Randomized hypothesis test. We're looking for test for single proportion. Remember, this was a test about a percentage. So we should not click mean or difference in means or any of those other ones, because that's going to mess it up. You have to click the right test. So we're going to test for single proportion. All right. Now we're going to go ahead and change the null hypothesis. Remember, our null hypothesis was pi or p equals 13%. Right now it's set at 0.15. So I'm going to change this to, sorry, it's set at 0.5. I'm going to change it to 0.13. 13%. That was our null hypothesis. Okay, now we need to have edit data. It told us to go to edit data and put in the count and the sample size. So the count was 39, and then the total sample size was 260. By the way, if we were doing a traditional test on this, we would want to be testing, one of the other assumptions for a traditional proportion test would be 10 successes and 10 failures, where there are at least 10 digital materials. Yes, there was 39. Were there at least 10 materials that were not digital? Yes, 260 minus 39 is a lot bigger than 10. So it would have passed the 10 successes and 10 failures. We could have used this data on a traditional test. All right, so there we go. And there's our 15% proportion right there. All right, so now again, in a randomized simulation, what you're trying to do is have the computer create thousands of random samples, all that have the same sample size as your original real sample. And then it'll be a way of measuring sampling variability and checking the tail and all of that. So we're going to click Generate 1,000 samples a few times. You can do as many as you want. You don't have to go crazy with it, but I usually do at least a few thousand. Okay, now was this a right-tailed test, a left-tailed test, or a two-tailed test? We said before that this was a not equal in the alternative hypothesis, so this would be a two-tailed test. So we're going to click two-tail. Now we want 90%, we want a 10% significance level. Now if it was a right-tailed test, that 10% should be just in the right tail. If it's a left-tailed test, that 10% should be in the left tail. But in a two-tailed test, it gets a little tricky. We have to split up the 10% into two tails. So that would be 5% or 0.05. So if I click on these top buttons, 0.05, and usually it adapts it, and you'll see here's your 90% confidence, which corresponds to 10% significance level, and you got 5% in this tail and 5% in this tail. You do have to write them as a proportion. Now we see where the tails start. Now this is a simulation of proportions. Okay, so this is a simulation of proportions. So what we're trying to do is, this is a way of figuring out whether the sample data significantly disagrees with the null hypothesis. So our sample proportion, our sample statistic was 0.15. That's the real one. By the way, don't get confused. This one that says randomized sample here is just a list of all the thousands of samples that we did. So, don't ever refer to this randomized sample here. It's always your original one. That's the real sample. That's what really happened. Okay, so what we want to know is 15% disagree with 13% in the null hypothesis. Well, again, because we've simulated the sample proportions, we now see that the right tail starts at 0.165. So for it to be significant, I'm going to need like a 0.17, 0.18, 0.19, 0.2. Also, the left tail starts at 0.096. So like 0.09 would be significant, 0.08 would be significant, 0.07, 0.06 would all be significant. Where does our sample statistic 0.15 fall? Does it fall in the tail or not? So notice we're not actually using a test statistic here. We could have calculated a test statistic and done it that way, but this is simulation, so we don't have to use a test statistic. We can just directly look at this sample proportion instead. Where's 0.15 on this graph? Again, it's very important to know the number line, right? It's all about number lines. Where's 0.15? Well, it's right in here, right? Is that in the red? Is that in one of the tails? If it was over here, it'd be significant. If it was like 0.18 or 0.19, that would be significant. If it was, excuse me, if it was 0.08, it'd be significant. But 0.15 is not in either of the tails. So that means it's not significant. Okay, so 0.15 does disagree with 0.13, but it does not significantly disagree. In fact, it's more what we would expect to happen just by sampling variability. Remember, this is a graph of sampling variability. So what we see here is it's not in the tail. Okay? So we go back to our answer here. Now, obviously, this simulation that's in the answer key is going to be a little slightly different. Actually, it looks pretty close to what I had in the one there, but there can be differences. Remember, what we said about sampling variability is random samples are always different. So when you do a simulation, you may not be exactly the same as the answer key. Like you might get 0.166 here or 0.095 here, you know. That's okay. You're going to have some sampling variability. So don't just go by whatever your graph shows. But all of them will pretty much show the same, that 0.15 did not fall in the tail. That means my sample data, 0.15, does not significantly disagree with the null hypothesis, 0.13. Even though 0.15 looks different than 0.13, it's really not that different. It's what we would expect to get by sampling variability. Now, how do we get the p-value? All right, this is not a p-value. 0.05 and 0.05, that's not a p-value. That's the significance level, right? Remember, we had a 10% significance level that we broke up. The higher ones are always the probabilities, but this is a significance level. So what you want to do, the definition of p-value is the probability of getting this proportion, right? Or more extreme by sampling variability. Well, here's sampling variability. So all I have to do now is put in this 0.15. Now it's a little tricky because I have two possible boxes. 0.15, this bottom right one or this bottom left one. Now, if remember our null hypothesis 0.13 is in the middle. So if my sample was lower than 0.13, I would probably put it in the left box. And if my sample was above 0.13, I'd put it in the right box. It's much easier when it's a right tail or left tail text, because then you can just put it in it only has one box to put it in. Two tails are always a little more tricky. So in this right bottom box, that's where the sample proportion goes. I'm going to go ahead and put in the actual sample data, the sample proportion. So I'm going to click that bottom box and I'm going to type in 0.15. Now what it's going to do is it's automatically going to figure out what's the percentage in the tail that corresponds to the sample data. Remember, that's kind of the definition of p-value. The problem is because it's a two-tailed test, we have to include both tails. So what you do is you add these two together, or in the old days you would multiply your tail probability times 2. It gives you the same just about. 0.188 plus 0.188. All right, so that's going to be our p-value. So if it was a right-tailed test, our p-value would just be 0.188. But if it's because it's two-tailed, you have to add these two tails together. So p-values for two-tailed tests are twice as big as for one-tailed test. Okay, so 0.188, 0.188, we're going to add those together and get our p-value. Looks like here's the one they did in the answer key. See, notice in the answer key it had 0.187. Okay, that's okay. That's because of sampling variability. Whenever you do thousands of random samples, your random samples are not going to be identical to the random samples they did in the answer key. Though this is pretty close. So 0.187 plus 0.187 would be 0.374. Ours was 0.188. So this would be 0.376 here instead of so we'd have about a 37.6% p-value. Notice again, your p-value on simulation might be slightly different than the one in the answer key. Again, that has to do with sampling variability. So if the null is true and 13% of materials are digital, there was a 37% probability of getting the sample data or more extreme because of sampling variability. That's the p-value sentence. Now, is that a high p-value or is that a low p-value? Is this number higher than 10% or lower than 10%, right? Or 0.10. 0.374 right here, 0.374. That's definitely higher than 0.1. And you can also see in the percentage, 37% is higher than 10%. So we have a high p-value. So remember how to interpret your p-value. If you got a high p-value, then we are going to what? Fail to reject the null hypothesis, right? It could be sampling variability. This sample data could just have occurred because of sampling. In other words, the population percentage really could be 13%, and we just got 15% because our random samples are a little different. Every random sample is a little different. All right, so now we have to think about the conclusion here. Now, again, this is one of the big things with this problem is this independence. If it really is independent, then we're going to be passing the assumptions. If it's not independent, then we're not passing really these assumptions. So, but we'll go ahead. We said we're going to assume this was independent. So if we assume this is independent and it passes assumptions, then we got a high p-value, and the null was the claim, right? Remember, in this one, the claim was equal to 0.13, and equal to is always the null. So when we failed to reject the null, we actually failed to reject the claim, if that makes sense. So we want to really say that we do not have evidence to reject the claim. In other words, the claim could be true. So conclusion, there is not significant evidence to reject the claim that 13% of materials are digital. The population percentage really could be 13%, since the random sample data does not significantly disagree with it. However, we do not have evidence. Now, how about this? Usually we don't really need the test statistic. We're done right now. But the problem actually asked you just to calculate the test statistic, just to give you some practice with it, right? To give you a little practice with it. And if you remember the z-test statistic, they put the formula here. Take the sample proportion, that was 0.15, minus the population proportion in the null hypothesis, that was 0.13, and then divide by the standard error. Now, where do we find the standard error? Well, if you look on my simulation here, standard error is right here. Standard error, and it says 0.021. Now, we could use a formula for that. Traditional statistics, we use a formula for standard error, but they actually calculated the standard deviation of this graph right here, of this simulation. And that's pretty close to what we would have gotten by the formula. Okay, so the standard error 0.021. So we can actually calculate the test statistic, even though we don't need it in this problem, just to kind of get a little practice. I think that's why they gave it to us here, okay? So let's see. So if I do 0.15 minus 0.13, remember to subtract them first. You're going to get 0.02. And then 0.02 divided by 0.021 is a little under 1. So we're going to get a positive 0.952. So this tells us that our sample proportion, 0.15, was 0.952 standard errors above, remember it's positive, that population proportion in the null hypothesis. And if you guys remember from your z-score, our study of z-scores, that's not a lot for a z-score. Usually, you're talking z-scores, usually we like them to be at least 2 or around 2, 1.96 or 1.645 or 2.576 were our critical values for z-scores. So this is not much. This is not a significant z-score. So that kind of matches with our sample data not falling in the tail and our p-value being high. Okay, so that was number 13 on section 3F. I hope it was helpful for you.